Okay, so we're going to talk about electron configuration here today. Electron configuration is the arrangement of electrons in an atom. If you remember from the last video, we described an atom as like a hotel for electrons. There are different floors, and then on those different floors are different sublevels, and then in those different sublevels are the orbitals. So here's the Bohr model of the atom, which has 7 distinct energy levels. Those equate to floors. And then within those floors are different types of sublevels. You have the S sublevel and the P sublevel. Then the S and P sublevels are made up of orbitals. There's also the D and the F sublevel, which I didn't picture here. We talked about all of that in the last video. So what we're going to do is we're going to arrange these from lowest energy, these sublevels from lowest energy to highest energy. And the way we're going to do that is we're going to create an F-bow diagram, where we're going to basically create a grid of all the different sublevels that exist. You have sublevels on the vertical axis, energy levels on the horizontal axis. On the S, all energy levels have an S sublevel. On the P row, all energy levels starting at 2 have a P. For D it starts at 3, and then for F it starts at 4. So you can see the grid that is generated. And from this we're going to be able to generate an orbital energy diagram. The way we do this is we start drawing arrows through the sublevels in the F-bow diagram. You can see the green arrow went through the 1s. I created the 1s orbital over on the orbital energy diagram. The second arrow went through the 2s. I create the 2s orbital on the orbital energy diagram. The third arrow goes through the 2p, and you can see that I've created 3 dashes for the 3 different p orbitals and labeled those 2p. It then also went through the 3s. Okay, so I create the 3s, and then the fourth arrow goes through the 3p. So again, 3 dashes for the 3p orbitals, and then it goes through the 4s. The next arrow goes through 3d, then 4p, then 5s. So since the D has 5 orbitals, the D sublevel has 5 orbitals, I'm going to create 5 dashes for the 3d, label that, and then the 4p, which will again have 3, and then the 5s. Now what you should notice here is that it doesn't go just energy level 1, then energy level 2, then energy level 3, etc. There's overlap, and that's because some of the orbitals are and sublevels are higher in energy in lower energy levels, meaning the 3D is higher in energy than the 4S. So the F-bow diagram gives us the complete orbital energy diagram that you see here. And the F-bow principle says that we will fill the lowest energy level sublevels first. On this orbital energy diagram, what we have is we have the orbitals represented by boxes. And each box, as you know, each orbital can hold up to 2 electrons. We're going to represent an electron with a half arrow. So hydrogen has just 1 electron. So what we're going to do is we're going to put a half arrow into the 1s orbital. And we're going to say its electron configuration is 1s1. The first one is the energy level. It's an energy level 1. The S represents the sublevel that the electron exists in, and it has 1 electron in that sublevel. So the electron configuration of hydrogen is 1s1. Helium has 2 electrons, so we're going to put a second electron into the 1s orbital. And we say that its electron configuration is 1s2. It has 2 electrons in the 1s sublevel. Now the Pauli exclusion principle is a rule that tells us that electrons with the same spin cannot exist in the same orbital. Okay, so they can't occupy the same orbital. This is why there's a limit of only 2 electrons per orbital. What you want to do is you want to think about an electron as spinning on its axis. If they spin in the same direction, they create a magnetic field, and therefore if they spin in the same direction, they will create a magnetic field, and they will repel each other out of the orbital. By spinning in opposite directions, as pictured here, they do not create that magnetic field, and therefore they can exist in the same orbital. But if you put a third one in there, it would spin in one of those directions and repel the electron out. So the maximum number of electrons per orbital is 2. So what I've done here is I've put out orbital energy diagrams of the first three atoms on the periodic table. You have hydrogen, which we did, which is 1s1, helium, which is 1s2, and then lithium, which is 1s2, 2s1. Here's boron. We're skipping up to 5 total electrons. Its electron configuration is 1s2, 2s2, and then 2p1. So you can see how these electron configurations build up. Now we get to carbon. And carbon has 6 electrons. And we have a choice. We can do it as it's displayed in choice A, where the electrons spread out, or we could put both electrons into the same orbital. Both of these will have the 1s2, 2s2, 2p2 electron configuration. But choice A is the correct choice. The reason is that the electrons repel each other. Therefore, when electrons can spread out over different orbitals of the same sublevel, they will, or they do. This is known as Hund's rule. Only after each orbital of a sublevel is occupied with the electrons will the electrons pair up. As you can see with nitrogen, 7 electrons, all 3 orbitals of the 2p have 1 electron. Then in oxygen, when we get to 8, we now pair up the electrons. So this is what electron configuration is. It's just a matter of putting the electrons in the individual orbitals. In order to do this, we need the Aufbau principle, which tells us always to fill this lowest energy sublevel first. We need to follow the Pauli exclusion principle, which tells us that no electrons with the same spin can occupy the same orbital, and we need Hund's rule that tells us how they'll spread out over the individual orbitals of the same sublevel. But doing this, we can easily calculate or determine